next speaker is Jiarul Midda, and he will speak on wrapping non-spherical vesicles at biomembranes.
Yeah. Good morning all, and thank you organizer for giving this opportunity to talk here. And today I'll be talking about wrapping of non-spherical vesicle at biomembrane. So let me begin with the introduction. So like how do cell exchange informations and materials with the environment? So this exchange typically happens by the exchange of particles. And the cell the membrane is typically kind of porous, like for small particles. So if we have like very small particle like ions or molecules, they can easily translocate through the cell membrane. But if the particles are large in size, so then the translocation happens via the biological process is called endocytosis or exocytosis. So this is the schematic representation. So in case of endocytosis, the large particle, so it come in contact with the membrane, get attached and get wrapped by the membrane and finally disconnect and or diffuse and go inside the cell. So this wrapping is like a key process in this endocytosis, and wrapping can be observed like both for living and non-living particles. So here is example of hard nanoparticles wrapped at lipid membrane. And this is the wrapping of a like elongated virus at the cell membrane. And for rigid particles, actually, this wrapping can be controlled by many parameters. Like it depends on the particle size, particle shape. If the particle is elongated, it depends on the particle orientation. It depends on the interaction between the particles and the membrane. And also it depends on the membrane's property, like the membrane stiffness and membrane tension. So here we ask the question that if the particle itself is deformable, so how does the deformability like controls the wrapping process? So for example, like in case of this virus, actually, so it's elongated virus, it has some deformability. So how does this deformability affect the wrapping process? Okay, so for that, we come up with a model. We use a continuum model system, and here we use the vesicle as a generic model system for deformable particles. So vesicle basically it's a large particle, so it's enclosed some amount of liquid inside, and outside it's a lipid bilayer, and the properties of the bilayer can be controlled. And here both the host membrane, like where the particles were attached, and the vesicle, we use like the continuum model. And here for numerical simulation, use this triangulated membrane model. So here the membrane we represent as a mathematical surface, and we triangulate it in terms of we triangulate it, and here which consists of like these black points are the vertices, is the vertices they connected by edges, and the small area is called facets. And the shape of the vesicle, which you are considering, so it's not necessarily it will be always spherical, but depending upon the osmotic pressure difference inside and outside the vesicle, it can be also non-spherical as well. And so how we model this non-spherical shape of the vesicle, we introduce a parameter, we call it reduced volume. So it's a dimensionless parameter, so it's the ratio of two volume, VV by V sphere. So VV is the volume of the vesicle with membrane area, so AV. And V sphere is the volume of of a vesicle, of a spherical vesicle with the same membrane area. So the maximum the value of this V is 1, so which represents a spherical shape of the vesicle. But if it's less than 1, so then it represents the non-spherical shape, as you can see here. Okay. So then, when this is a typical picture, we observe, for when the vesicle is partially wrapped at the lipid at the planar, initially planar membrane. This the gray color is the initial planar membrane, which has a bending rigidity kappa p and tension sigma. And this elongated particle is a vesicle which has a bending rigidity kappa phi. And so when it is get wrapped, so it's deformed the membrane, and we can calculate the deformation energy by using this Hamiltonian. We called Helfrich Hamiltonian. So which is a different term. So the first term we call the bending. So it's associated with the planar membrane, which has bending energy and surface energy. This is the bending energy of the vesicle. This is the addition energy. And these last two terms actually we have added to the Hamiltonian to control the shape of the vesicle. So these are the Lagrange multiplier basically. So it's which controls the area and volume of the vesicle. So here we introduce few dimensionless parameters to represent the results. We call it reduced membrane tension, reduced addition strength, and the wrapping fraction. So wrapping fraction is basically that how much fraction of the particle is attached. So this AD divided by AV. So the total area of the vesicle. So how do we perform the simulation? So we start with a very coarse triangle. So and we put for both for the vesicle and the membrane, and then we minimize the energy. And during minimization, to reach towards the continuum model, we refine the triangles. And during this refinement, we also use the dynamic triangulation so that the edge of the triangles they can move within the nearest triangles, and that maintains the fluidity of the membrane. So then here is the result. So we take different non-spherical shape of the vesicle, we put in the membrane, and then we look at, by controlling this wrapping factor as a control parameter, we look at the wrapping behavior. So here today I'll discuss about this, the oblate shape vesicle because of the time constraint. So I put the vesicle and I changed the wrapping fraction from 0 to 1. 0 means non-wrap state, F equal to 1 means complete wrap state. And and when we go from this non-wrap to complete wrap state, we observe different partial wrap state. So when the wrapping fraction is 0 to 0.5, we call it shallow wrap, and when it is 0 to 0.5 to 1 in between, so we call it deep wrap state. So what we observe here, the wrapping always starts with the lowest curvature region to minimize the energy. And during this wrapping process, we have observed the orientation change of the vesicle. So initially, the major axis it was perpendicular, but at higher wrapping fraction, it flipped 90-degree rotation we have observed. And also we observe another interesting thing is the shape change of the vesicle. You can see initially it was oblate shape, but it goes to this tomato side shape. Again, it go back to the this oblate, this vertical oblate state. So, and this shape changes is not allowed in case of hard particle. So, and also you can see that the vesicle is locally deforming the membrane. So we can calculate the deformation energy as a function of wrapping fraction. So, so this black this line is representing the so basically this is without addition strength. So the deformation energy it increases with the increase of wrapping fraction. So and the lowest energy appears at Fw equal to 0. So that means the non-wrap state is the stable state of the vesicle. But if you add addition energy which is proportional to the wrapping fraction, and then we observe the different energy, the minima in this energy landscape. So those are the which corresponds to the different partial wrap state. So the first stable partial wrap state appear at point A, so which we call the binding transition, and where the first time the vesicle stably bind to the planar membrane. Then as we increase the addition strength further, we observe the coexistence of two partial wrap state at point B, which is a shallow wrap state, and the C is called the deep wrap state, which is separated by energy barrier. So which we call shallow to deep wrap transition, and the transition from B to C is called shallow to deep wrap transition, which is discontinuous here. We are also with the further increase of addition strength, we observe coexistence of two deep wrap state, which is also separated by energy barrier. So this deep wrap to deep wrap transition is also discontinuous. And finally, it go from this D2 to E, which is called the enflowerment transition, which happens smoothly, which is continuous here. So by analyzing this deformation energy, we can predict the different energetically stable state, and we can also construct different wrapping diagrams. So here I have constructed one such wrapping diagram in the addition strength versus so this is KR is the basically it measures the the bending rigidity ratio between the vesicle and the membrane, and low means it's soft and high means it's rigid. So here we observe that the binding transition decreases, the addition strength for binding transitions decreases as the vesicle becomes softer, but for the enflowerment transition it increases. That means softer vesicle easily get attached to the membrane, but the complete wrapping is difficult. And also we observe this, when the vesicle is softer within the deep wrap state, the vesicle changes shape, and but for hard particle only orientation changes observed. Similarly, we look at the effect of membrane tension. So there we observe that the binding transition doesn't depend on the membrane tension, but and the shallow wrap state becomes the stable state, and the deep wrap state vanishes at tipple points. So we observe two such tipple points. The first one, where we observe two deep wrap state coexist with a complete wrap state, and this is the second tipple point where one deep wrap state, complete wrap state, and shallow wrap state coexist. And the interesting thing is the optimal addition strength for complete wrapping occurs at finite membrane tension, and this happened at the first tipple point. So with that, I'll conclude. So we have studied the wrapping behavior of a non-spherical vesicle. We have looked at the shape change and orientation change of the vesicle during wrapping. We have observed that the softer vesicle easily get attached to the membrane, but complete wrapping is difficult. Also, we have observed that the finite membrane, and also the deep wrap state vanishes as a typical point where we observe coexistence of 3 stable phase, and the finite membrane tension leads to the optimal adhesion strength for complete wrapping. And with that, I'll acknowledge my students who did this work, and thank you all for listening, and I'll be happy to take questions.
Thank you. Once again.
Very nice presentation. So, have you used Surface Evolver for modeling of your?
Yes.
So, my question is, what are your boundary condition of the membrane? Is the free?
It's an open boundary condition. So like the tension of the membrane is fixed. So like when the particle is getting wrapped, so additional membranes can come from the outside.
Okay.
Because we are considering the planar membrane is very large, so the membrane tension is not changing during this wrapping process.
Okay, thanks.
Yeah.
Thank you, Diaru, once again.
Okay.
And we can move to the next speaker.